Okay, hi everyone. So my name is Agus. I'm a research associate at CCRC. I'm also affiliated with COE as an associate investigator. So I've been asked to present something about modes of variability in climate models. But given just half an hour, I'll just focus on ENSO, which is the research topic that I've been following for the past few years. So I just want to start off with a take-home message before everyone feels sleepy, and I might not be able to finish in time as well, maybe. So first, there are 5 points. First one, climate models can simulate ENSO overall, yeah? But representing realistic ENSO is very hard because it's a highly coupled system, and there are various factors that influence ENSO variability. And it could be internal within the Pacific Ocean, or it could be external as well, such as the Indian Ocean or any other variability from other basins. And there is improvement from CMIP 3 to CMIP 5 in simulating ENSO, although it's not much, but there is still improvement. But for the improvements to be made would come down eventually to improving the mean state of the model. And that could involve improving cloud simulations. And of course, steps taken to improve ENSO simulation can improve other things as well. Perhaps better improvement of the southern annular mode or the Indian Ocean dipole. Okay, so just to start off, the idea of modes variability is all an affair of temporal scales, spatial scales, and where, or the locations where you're talking about. So ranging from daily time scales to millennial and longer. On the intra-seasonal time scale or annual and shorter, you have a Madden-Julian oscillation, for example, the monsoon systems. On intra-annual time scales, you have the annular modes, ENSO, Indian Ocean dipole, and of course interdecadal. Most people, I would presume, know there's a ENSO-like pattern which is called the interdecadal Pacific oscillation. And on much longer time scales, we have the bipolar seesaw, which you can see in the Atlantic. It's when you have a cold North Atlantic, you have a warm South Atlantic, and it's involved ocean feedback. Okay, so there are ways of characterizing modes of variability, and people usually use empirical orthogonal function to extract the both space and time evolution of the modes variability. And we have to remember that modes of variability arise due to different media of the climate system of the Earth. There's a land, ocean, and atmosphere. All these interact, and this give us various modes of variability. But how to extract them? And if you use these techniques such as EOF or just simple standard deviation, you just do a standard deviation of the Pacific, you can extract an ENSO pattern like this. There's an EOF presented as regression maps. And there's the Indian Ocean dipole, which is very strong in this particular model, Saromac 3L, which I use in my paper, compared to OPS. But then you can also look at the temporal evolution. How do you extract that? You just take the time series and do spectral analysis, wavelets. So you can see what sort of time scale it has. For example, ENSO has a time scale of 3 to 5 years in the OPS. In some models could be longer or shorter, as you will see later. And when you do EOF, you always check the composites, because EOF is a highly statistical, is statistical technique, and there's a criteria or constraints. If the first mode and the second mode are orthogonal, and these modes might not even be realistic. There is no physical reason for it apart from statistical. So if you cannot see any years that do not show such patterns you see in the EOF, then it is likely to be statistical. But IOD is a physical mode because you do composites, and you can see very strong patterns when it occurs with El Nino. positive IoT. Very cold in the Eastern Indian and very warm in the Eastern Indian, in the Western Indian Ocean. So what is ENSO? ENSO is the most dominant mode of variability in the Pacific. And to understand that, you need to understand the anatomy of the Pacific Ocean. You have a cold tongue in the Eastern Pacific. There's a normal condition. So when you have a cold tongue here, cold and warm pool, there's a convective processes going on there, and that drags the winds to flow to the west. Yeah? And when the wind flows to the west, it lifts up the thermocline in the Eastern Pacific and lifts the thermocline down in the Western Pacific. But when El Nino occurs, this situation reverses. So you have the wind flows to the east, and the thermocline slope flattens. And the thermocline slope is very important, and the winds and SSTs, and this form Birkner's loop, positive feedback. So when the wind flattens, the thermocline flattens, there is more warming in the subsurface. It enhances the SST warming in the Eastern Pacific, and that warming further enhances the weakening of the winds and suppress upwelling. So the warm SST becomes stronger and stronger. And what pulls it down? So as El Nino grow, what actually brings it down back to normal? And this can be explained by different paradigms. And the most famous one, which is the recharge oscillator paradigm, is when during El Nino you have in terms of anomaly, the thermocline is reversed, and then it will be followed by discharge, because when the wind stress anomalies flows to the east, the geostrophic current, the Schwager current flow goes forward, right? And so it discharges the whole warm water volume in the Pacific, and that results in a how do I go back? In a colder Pacific. When you have colder Pacific, it preconditions for La Nina development, which is the cold phase of ENSO. And then during La Nina, the wind flows to the west like normal condition, and that recharges the warm equatorial Pacific. And that warm condition will precondition for the next El Nino development. But we need a tool, because this is very highly coupled system. And yeah, so it's quite complex, right? So we're trying to describe the evolution of temperature. So there's so many variables, but the first equation there is the heat budget equation, which describes the evolution of temperature anomalies. And I just cut it short. This can be written as that very simple linear equation, right? As a function of temperature anomaly. And this term here is the stability term, which is the growth or damping rate. And then there's the phase change term. And that Birkner's feedback term can be decomposed into 5 components. The first one is the damping. So there are 2 damping, which I highlight there in blue, by the mean currents and by thermodynamic damping. So if you have warm anomaly, the acid heat flux will try to cool it because of clouds, because of latent heat. And then you have 3 thermocline feedback terms. First is by the current anomaly, second by upwelling anomaly, and the third by thermocline anomaly. And this can be further decomposed into its respective components, which is as a function of acid coupling between atmosphere and the ocean. So ENSO cross-climate models, following up from that formula, which is the BJ index formula, there's a good correlation across CMIP3 and CMIP5 models. That is, if you correlate BJ index against ENSO amplitude, standard deviation of Nino 3.4, for example, there's a good correlation, meaning that when the stability index is becoming more positive, the ENSO in the model tends to be stronger. So it just tells us that this formula is useful for understanding, for linking ENSO amplitude across models with what is going on in the governing feedback mechanisms, which is the current feedback, the wind and current feedback, the wind and thermocline feedback, and upwelling. This is a paper by Kim et al. 2013. Most of these slides, the following slides, will be based on their paper, which is in press, and there's another one in climate dynamics as well in press. So this is the other one here. I think it's French. I don't know how to speak French. So I think Boulanger, something like that. Overall, there's an improvement phase line between CMIP 5, which is the red, and CMIP 3 against OBS, which is the black dot there. So the range of uncertainty is reduced towards observations, but still it's only quite minor, right? And if you look at the feedback processes governing the ENSO amplitude, this is the first feedback term. The blue is CMIP 3, red CMIP 5, and that's observation, which they use soda for this analysis. There's not much change there. The second term is thermodynamic damping. It's way off, right? CMIP 3 and CMIP 5. And all these three positive feedback terms, they severely underestimate the zonal effective feedback, which is the coupling between the wind and currents, and also underestimate the thermocline feedback, which is the most dominant feedback in terms of the Bjerknes, in terms of the recharge oscillator. Okay, so I want to highlight these two feedback here and thermodynamic damping, which is basically acid heat flux that try to damp the SSE anomalies. It could be related to clouds processes. So let's just cut it short. So what we can do is, they want to find out what controls, which governing process controls the intermodal variations in thermocline feedback and zonal effective feedback. And you can do intermodal correlations. And it turns out the highest correlation is associated with beta H, which is the coupling between the wind and thermocline depth, right, the slope. And beta U, which is the current and the wind. Okay, these are the two main factors that cause intermodal spread, and it can cause underestimation as well. And this comes down to biases in the mean climate. If you correlate all those beta H and beta U, this for thermocline depth is the mean climate, right? So long-term mean. So it tends to be, to improve beta H, to make it closer to observations, you need a positive and negative. It's a flatter thermocline. And if you have flatter thermocline, you will tend to improve coupling between the wind and current as well. And thermodynamic damping and SSE is negatively correlated. That means the more SST warming you have, the climate model have in the Eastern Pacific, you will tend to improve thermodynamic damping. It's just implying that current climate models are too cold in the Eastern Pacific. If you can improve that, then this will improve. And that is usually associated with a cold tank bias. And that in turn associated with too strong trade winds. And we have too strong trade winds and try to weaken it. If you weaken the trade winds, as I mentioned before in the intro, you will tend to have a flatter thermocline, and that will perhaps improve beta H and beta U as well, right? But if we look at the thermodynamic damping term, what caused the spread of that? What caused the spread in climate models in simulating SE feedback, SE flux feedback? And it comes down to shortwave feedback. So the spread across CMIP 3 and CMIP 5 is not due to latent heat flux feedback. It's mostly quite close to observations, but the short wave feedback is severely underestimated, and many of the models even simulate a wrong sign in the short wave feedback. It's supposed to be, if you look at the orbs, it's supposed to be a damping term. See, that's negative, right? But some of the models simulate a positive feedback. That means the cloud will act as a positive feedback, creating the warming during El Nino, which is wrong, right? And the short wave feedback term is actually nonlinear. If you look at the orbs, which is the green dots there, and that's as a function of sea surface temperature normally. For negative normally, La Nina, it's a positive feedback. But for El Nino, it's a damping. Some of the models are like that, which is all the black lines there, but still underestimate the damping. But a lot of the models, they consistently show positive feedback, right? This one here, and they label it as which is subsidence. So if you have a really cold SST anomalies compared to orbs, it will tend to have more stratiform clouds. And when you have a SST anomaly that is warm, the stratiform cloud disappears, and that will make the SST warmer. So that's positive feedback. And that's on the other extreme is the convective group, which shows always a damping, always a negative feedback, even La Nina, right? And that is this group of models. They tend to simulate cumulus clouds. But the best one will fall in this mixed group. And there's a correlation with this the stronger the nonlinearity, it tends to correspond with stronger ENSO. That means if see, the mixed one is black dots, subsidence and the convective groups are the blue and red dot. These tend to have very weak ENSO. So the system is already either cold or too warm in the Eastern Pacific, and the ENSO is weak. So it never switches into a different regime. It's always in either subsidence mode or convective mode. But the mixed one tends to have stronger ENSO, so you can switch the system back and forth. And this nonlinearity in shortwave radiation peaks in March, April, May. And the models that can produce this will tend to have a better ENSO seasonality, which means ENSO variability will peak in December, January, February, and weaken in March, April, May. And these plots down here is showing that there's a relationship with the equatorial SST climatology. So the convective groups, which is always simulating cumulus clouds, tends to be too warm compared to ops, which is the green line. And the mix is somewhere in between the subsidence, which is too cold, and the convective group. So if we look at CMIP 5 and CMIP 3 in terms of the SST climatology along equatorial Pacific, the CMIP 5 is improved a little bit towards observations, which means, in the Western Pacific, it shows it's warmer than CMIP 3. That means it has a reduced cold tongue problem in the Pacific, right? And that will translate to weaker trade winds. So if you have weaker trade winds, tend to have a, flatter thermocline slope. And that's probably the reason why the ENSO is better. If we look at spatial patterns of ENSO across the models, this is for CMIP 3. The first panel here is for the observations. It's really confined in the Eastern Pacific. But many of the models, this variability extends far to the west. This is related to the cold tongue problem. The cold tongue is supposed to be in the Eastern Pacific, but in many of the models, it extends far to the west, which also means it's a colder warm pool. And in CMIP 5 is improved. If you can see here, this is warm Western Pacific, Central and Eastern Pacific for the onsets, peaks, and terminations of El Nino and La Nina events. During the peak of El Nino events and La Nina events, the OBS shows peaking in Eastern Pacific. And CMIP 5, it has more frequency, more occurrences in the Eastern Pacific than CMIP 3. So it's a big, it's a notable improvement in that sense. If you look at ENSO period, again, this is the observations. The ENSO is always in the 3 to 7 years band. Some model like CCSM3, it simulates very, very strong biennial tendency at 2 years. And some of the models show very, very weak variability and very long ENSO, like this one. Just focus on the black one because the red one is projections. And I just want to do a case study which is based on, hang on, this slide is just show that across the CMIP 3 and CMIP 5 there's a slight improvement. In this SM3, as you can see here, there's a very, very strong biennial tendency, right? And previous studies have attributed it to, if you look at the observations, the structure, the meridional structure of the wind stress anomalies during El Nino is wide, okay, compared to CSM3, which is very narrow, confined to the equator. And this is consistent with the idea that, the broader the meridional width of the wind stress, it will tend to force off-equatorial Rossby waves. So the Rossby waves tend to be slower in the off-equatorial Pacific. So if you're reaching out further away from the equator, it will spin up slower Rossby waves, which then reflect along the equator slower than CCSM3 to terminate ENSO events. And that probably can explain why the ENSO in this model is very rapid compared to observations. But also studied by Yu et al., 2009 Journal of Climate, the improved, this biennial bias it disappears once you decouple the Indian Ocean. So they actually decouple the Indian Ocean by removing SST bias. And by doing that, the biennial component of the monsoon rainfall, in Australian monsoon rainfall, Indian monsoon rainfall, also severely weakened. And as we all know, well, not all of us know, that monsoon variability, wind stress anomalies project strongly on the Western Pacific winds, and which have a role in terminating ENSO events. Okay, so this is a diagram from Chai et al. I didn't write it there. This is from Chai et al. Journal of Climate, 2011. We want to, just want to highlight the ENSO teleconnection here. So there's a significant correlation between ENSO and the southern annular mode, which is in negative. If you have El Nino, you will tend to have a negative SAM, which is a equatorward extension of the wind stress. But the intermodal correlation with CMIP 3, ENSO standard deviation correlated with correlation ENSO and SAM, there is a very high correlation, minus 0.65. It indicates that, if the model has stronger ENSO, it will tend to have more occurrences with southern annular mode. But But it's not the other way around, yeah? Because the correlation is very weak. If you correlate the standard deviation of SAM, then there's a very, very weak slope. That means that the subnonlinear mode does not influence ENSO. So ENSO has a very big influence on SAM. So simulating ENSO will probably improve subnonlinear mode. If you look at the magnitude of subnonlinear mode, it tends to be is too strong against observations, which is triangle there. I'm not sure why, but it's probably related to ENSO or some other, or mean state biases. In terms of Indian Ocean dipole, the ENSO can induce Indian Ocean dipole events. The stronger the ENSO, you will tend to have more occurrences with Indian Ocean dipole events. How about the other way around? Can the IOD affect ENSO? This plot here on the right-hand side suggests that it can. There's a strong correlation, means the Indian Ocean dipole might have positive feedback on ENSO, which have been found by previous studies. And this is a study that I did last year. So there's a strong correlation between ENSO and IOD and ENSO amplitude. But when you remove the Indian Ocean as if feedback, the ENSO tends to become stronger in this model that I use, which is Cyromax 3L. And this is a function of ENSO versus IOD in control. That means if certain epochs have lots of ENSO and IOD co-occurrences, that means the ENSO is less damped. When the ENSO and IOD tend to co-occur less frequently, there is more damping by the Indian Ocean. That's why if you remove the Indian Ocean, the ENSO in the model becomes stronger. So with that, I finish my talk. This was the take-home message, which I don't think I'll repeat again. Thank you.
Question?
Yeah.
You talked about the whole coming price using 3 moles. I'm not sure if you mentioned that seemed high. Have they shown any improvements in?
From those plots, I think there's a little bit of improvement, but not much. I don't think it will eliminate all the ENSO biases. It's not enough. Yeah, Jensen.
There's a slide you describe the feature index relationship with the ENSO amplitude in sigma 3 and sigma 5. It seems in sigma 5 this relationship is not very good.
Yeah.
So do they have any explanation for this?
If you look at the plots again, there are 2 outliers there. This one, right? Yeah, if you remove this, the correlation becomes significant, 0.58. And the reason is likely because this formula is not perfect, right? It just describes the linear system of ENSO. But in these models, there are perhaps 2 strong non-linearities that is not captured by the formula. That's probably why. But in terms grossly, in gross term, in gross sense, ENSO can be described by linear feedback interactions. But of course, non-linearity is important as well. It's probably the MRI one. MRI and MPI, I think.
You had a plot where you showed longitude on the x-axis and you showed SST curves for cement 5 in the arm.
This one?
Yeah, but why do the models really push up the SST like on the far east?
This one here?
Yeah, why do they do that? I'm just curious.
Oh yeah, that's too warm, right? Because there's not enough coastal upwelling.
No, not coastal.
Yeah. And it's probably related to the resolution of the model. If your model resolution is tend to be coarse, then you won't resolve all these coastal processes very well.